So in this video, I'm going to explain the calculations for the equilibrium experiment that we did in Chem 102. So the idea is that phenolphthalein, which is an indicator which we use for this experiment, is a weak acid in aqueous solutions. And if In represents just an indicator, then the regular equilibrium expression looks like this. It dissociates into a proton and its conjugate base. And the Ka for phenolphthalein will look like this. And that's our goal for this experiment, is to find the equilibrium constant for phenolphthalein. So we're going to do it two different ways. One, we're just going to find all three of these values, plug in, and get our Ka. And the other way is we're going to use the Henderson-Hasselbalch equation, which I'll do in just a minute. So that means the first way we need three different values: the concentration of hydrogen ion, the concentration of the conjugate base, and the equilibrium concentration of phenolphthalein that's not deprotonated. Well, this one's easy, the hydrogen ion concentration, because you guys remember you measured the pH. And so to get the hydrogen ion concentration, it's just 10 to the minus pH. Now, you did 5 different buffer solutions, so you're going to do this 5 different times. Get 5 different values for Ka and take the average. Now, to get the concentration of the conjugate base, you measured the absorbance with a spectrometer. And this equation right here is called Beer's law. It says the absorbance of light that's passing through a solution is equal to something called the molar absorptivity of that solution times the lambda, which is the path length, the distance through that solution, times the concentration in moles per liter. So you need the molar absorptivity. And so that's what the pH 11 solution was for. And that's the only thing you used the pH 11 solution for, was to find epsilon here. So if we rearrange Beer's law, we can solve for epsilon. And we know at pH 11, because it's so basic, all of the indicator has been converted to its conjugate base. In other words, there's no protonated form of phenolphthalein left. It's all in the deprotonated form, which means that the initial concentration that we put in there is the concentration of the base. Now we can calculate that just because Matt put the concentration of the phenolphthalein on the bottle, and it might not have been 2.01 times 10 to the minus fourth. It depends upon when you got your phenolphthalein, but you should have written it down. If not, just use this. And you diluted it 2 to 20. Put 2 mils of the phenolphthalein plus 18 mils of water, so 1 to 10. And that's just the dilution equation, and that gives you the initial concentration of the phenolphthalein. And at pH 11, that's equal to the concentration of the conjugate base. We can get that. That goes as C in Beer's law. The path length, lambda, that's what you measured with the calipers. Make sure you put that in centimeters. And you also recorded the absorbance from the spectrometer. Put all these 3 in, and that'll give you your epsilon. And that's what you'll use. That doesn't change, that stays. And that's what you use for epsilon in the rest of the calculations for this part. So now Beer's law again. Now we're going to use Beer's law to calculate the concentration of phenolphthalein in each of the 5 buffer solutions, pH 9.2 through 10. And it's just the absorbance that you measured divided by the epsilon that you calculated just a minute ago, times the, on the bottom is the path length, which you measured. Plug all these guys in, and you're going to get 5 different concentrations of the conjugate base. That's the second part in the Ka expression. The third thing we need is the equilibrium concentration of the unprotonated form of phenolphthalein. Well, all that is the how much that's at equilibrium that's still protonated, is how much we put in initially minus how much was deprotonated. And this, the initial concentration, is going to be the same for all 5 trials. It was always whatever your initial the concentration of phenolphthalein that Matt wrote on the bottle is, times 2 over 20. And so you're going to, because you had 5 different values for your concentration of the unprotonated form, you're going to have 5 different values for this, 1 for each pH. So now we have 5 values for the hydrogen ion concentration, this and this. Plug in, you get 5 Ks. You're just going to take the average of those, and that's what you're going to report for this part of the calculations. Now, the other way we're getting the Ka is with the Henderson-Hasselbalch equation. Now, I've just switched this around a little bit. Usually we see it as pH equals pKa plus log of the base over the acid forms. Here's switched around because the dependent variable is pH, then the independent variable here is the log of the concentration of the base over the acid forms. So this looks like a straight line, y equals mx plus b, where m is the slope is 1, x is the log of the base over the acid form, and the y-intercept b is the pKa. So all you have to do is you're going to take your spreadsheet, Excel, Calc, whatever you're using, and you're going to plot on the y-axis the pH, on the x-axis the log of the base over the acid forms, get the equation of the best fit straight line. Whatever b, the y-intercept is in that equation, that's your pKa. To get your Ka, it's 10 to the minus pKa, and you only get one of these. And that is that.